Hello, everyone. Welcome back from the break. And I'd like to introduce our next talk, TornadoVM, Harnessing the XPU Power from Java by Juan Famero. Hi, Juan. Please go ahead. And also to the audience, feel free to post your Q&A in the Q&A tab, and I will make sure I let people know at the end. All right?
Thank you very much, Rui. It's a pleasure to be here in this conference and be able to talk about the TornadoVM project. So what is TornadoVM? So TornadoVM, in a nutshell, is a Java parallel programming framework that allows us to offload a subset of Java, to run on GPUs, FPGAs, CPUs, and even custom hardware accelerators, for example, RISC-V accelerators. So if you haven't heard about TornadoVM before, don't worry, we'll cover the basics, what it is and how you can start using it. And if you have heard about TornadoVM before, well, I have some new things to talk about. So we have something for everyone, right? Okay, so let's get started. What I'm gonna do is I'm gonna show you first a sneak peek on performance. How fast or how slow is these solutions compared to native? That's what we care about, right? Because we want to accelerate the application. So I'm gonna show you some performance analysis at the very beginning and see and study and analyze the potential performance and analyze the gaps, potential gaps that we might have and why we might have those. Then I'm gonna describe the overall project, and I'll give you an overview of the project. I'm gonna start with demos, with some code examples, how to start running TornadoVM applications. So by the end of the talk, if you're interested, you can pick Tornado, it's also open source, and start writing your kernels for running on GPUs. And then I'm going to talk about new things that we have been doing lately. One of the things is we integrate Tornado with what is called One API Construction Kit from CodePlay, and this allows us to run not only on GPUs, but also on CPUs from Intel, ARM, or even RISC-V. So I'm going to show you performance analysis and even a demo running on RISC-V accelerator. And finally, I'm going to show you some of the standalone technologies that Tornado has created. So apart from the whole project, Tornado, some of the subcomponents or submodules can be used as a standalone. And in fact, some of them are being used by third-party people. For example, there is a new project in OpenJDK that uses the code gen that is written by, that we use in Tornado. We developed for Tornado. And I will also show you an example of how to run LLMs with one of the technologies in Tornado and in Tornado. So I hope I piqued your curiosity. So let's get started. So first of all, as I mentioned, I'm going to run some performance analysis and see how fast is Java compared to other solutions and how fast potentially could be Tornado compared to native. So I'm going to run this matrix multiplication. I think for this conference, everyone understands this application. It's very important today because this thing called LLM, AI, etc. is one of the key kernels, matrix vector, matrix multiply. So what I did was to run this application on a desktop i7 12th gen with a very big matrix size. And I use, to run on the hardware accelerator, I use an RTX, an NVIDIA GPU 3070, which is kind of normal these days, right? It's not the fastest one. It's kind of in between. By the way, practically the whole source code I'm going to share today is available. I'm going to put it in the slides as soon as we go through it. So, first I'm going to show you here the performance of Java in peak performance. That means that has been already warmed up, and I show you just the peak performance after Java compiles the code. And it took 2 seconds, more than 2 seconds to run the single-threaded application. Single-threaded though. Let's run the multi-threaded application. What do we get? We get 10x. This is Java, just Java, no GPUs, nothing else, just Java running the multi-threaded application on this system. And we get 10x over the previous version. That's good. But what if we run OpenCL code directly? See OpenCL code. Well, we get 100 times, more than 100 times faster, 140 times faster compared to Java, and way faster than, more than 14 times faster compared to parallel Java, multi-threaded Java. And the goal here for us is to go from the sequential application down to this code. Is it possible? Well, that's what we're trying to do in Tornado. So Tornado can support matrix multiply. That's a very easy type of kernels for Tornado. And if I run it, I get this performance, 920 times faster compared to Java. And it's more than 6 times faster compared to OpenCL C++. What's going on? It's something weird here, I'm a compiler engineer, so we have to be careful how to compare things, right? So what's going on? Okay, TornadoVM is more than just a translator. It also optimizes the code, and optimization means just-in-time, so compile optimizations and runtime optimizations. So it's giving you more than simple code translation. While on the OpenCL one, I just wrote the naive matrix multiply. Why did I do that? Because the code in Java is the naive matrix multiply. So what's going on? In fact, Tornado applies many optimizations. So let's try to recreate what Tornado does. One of the things that Tornado does is to apply loop interchange. This is a very old compile optimization. Just swap two loops. In this case, I think the outermost loops, I believe, and we get a bit of extra performance, but still it's not as fast as Tornado. What's going on? Tornado also applies FMA optimizations. So it's an instruction that performs fuse multiple add in a single instruction. Still, it's not faster than Tornado. What's going on? Well, Tornado also applies some compilation flags in the OpenCL part. Still, it's not faster. And it also applies some loop unrolling factor, but it's not even faster. One thing is also, apart from compile optimizations, Tornado also applies some heuristics to decide the amount of threads to run, the block of threads. If I apply the same tuning, then I get faster than Tornado. In fact, all of these are the optimizations that TornadoVM applies. If you know matrix multiply and you know OpenCL or CUDA, you know that the typical one is also apply local memory, loop tiling, etc. This is not applying Tornado right now, but we have proof of concept, actually a publication about how to do this within the compiler, but it's not upstream just yet. But what I want to mention here is, okay, if you program in CUDA, OpenCL, one API, probably you are used to, it's part of your job, you just assume it, okay? That part of the job is also optimization. But if we want to go from Java or any other managed runtime language, Java, Python, Ruby, JavaScript, etc., optimizations are not part of the usual workflow. So we have to be careful and not deal with this as a part of the user experience or the user part of the code writing. We have to do it manually. Sorry, the compiler has to apply all of this in order not to do it manually. So why is this? Because, okay, as you know, OpenCL as well as CUDA, as well as one API, code is portable, but performance is not portable, right? So there are many things that you can do to achieve performance portability. And Tornado is trying to go in that direction, okay? Also to have an experience that is fast enough for many of the Java developers. And not just Java, because Tornado is on top of JVM, and you can run any other JVM language, like Python, for example. I will show you an example later on. Okay, so I hope this piques really your curiosity. Let's go into the details. Let's talk about Tornado. First, I'm going to give you an overview. So what is Tornado? TornadoVM is a plugin to an existing JDK. So despite that the VM in it, in the name, the VM is because, technically speaking, it's a nested VM. So it needs a host VM. That's the Java virtual machine. Okay. So you need an OpenJDK-based distribution. Could be OpenJDK, GraalVM, Amazon Corretto, Windows JDK, Red Hat Mandrel. No modification whatsoever in Java. Just take that virtual machine and run and plug it in with Tornado. Okay, as easy as that. And with that strategy, that can give us access not only to optimize code for CPUs, but also optimize code for heterogeneous hardware, GPUs, FPGAs, from many different vendors, even RCPUs, RISC-V. I will show you an example later about this later on. Okay, so what Tornado employs under the hood is a set of backends. In fact, Tornado, as it is right now, today, has 3 backends. One for CUDA targeting from Java bytecode. So entry point for Tornado is the Java bytecode, okay? Not even the Java source code, it's Java bytecode. Everything happens at runtime, everything. So from Java bytecode down to CUDA PTX. PTX is assembly code for CUDA programs. Java bytecode down to OpenCL C code, or the new one that we had recently in a collaboration with Intel is from Java bytecode down to SPV binary. And then we can dispatch this SPV binary through either the Level 0 API or the OpenCL runtime. So if I go deep a bit more, what TornadoVM offers is the following. It has a set of APIs and a runtime system. Why it offers an API? Well, Tornado does not auto-parallelize the application. It exploits parallelization. So we need an entry door, okay, from the developer side to identify where the parallelism is located, which functions or methods you want to offload, and so on, right? So to do this, we offer some of the data structures. The key concept in Tornado is the concept of task. What is a task? It's a Java method, as simple as that. Each task is a Java method. Within the Java method, you can annotate your code. I will show you an example later on how to do so. And you can create a group of tasks, meaning a group of methods, to run all together on the accelerator. And that's what we call a task graph. And then you can also create an execution plan. An execution plan is basically it's a data structure that orchestrates, that help you to define where the execution is going to be, the optimization you're going to apply, if you want to apply or not. Okay, I will show you an example about all of these later on, so don't worry about all of these names. So what's happened under the hood in the runtime system? Well, there are a few components. The main one is the execution engine that orchestrates everything. And one of the tasks within the execution engine is to optimize the task graph to avoid extra copies, right? If you have an array that you need to copy in and out from the region, but you never read from the outside, for example, that's optimizing the graph optimizer. So Tornado tries not to send more data than you need or get back more data than you need. And the execution engine also handles memory for you, handles compilation for you, etc. So the just-in-time compiler is an extension of the Graal JIT compiler. Not sure if you know Graal. Especially in this conference, is more Java specific. But Graal is a new just-in-time compiler for Java, written in Java, and is as fast as the C++ compiler right now. And it's actually in production. So some companies like Twitter or X right now is using in production. So whatever you tweet is actually run under the hood. And you can run many programming languages, not just Java, but also Python, Ruby, JavaScript, WebAssembly, and so on. So we took the Graal JIT compiler and extended, it's also open source, and extended with a backend for OpenCL, for PTX, and for SPV, as I mentioned before. So we have different talks explaining in detail the JIT compiler, and also we have some publications in which we talk in detail. So I'm not going to focus about this. I'm going to focus more on the usability of the TornadoVM project rather than the technology under the hood. Let's focus now how you can use Tornado if you want to use it. So we have different set of APIs. Why do we have different APIs? Well, when we design Tornado, we ask the three following questions. The first one, how do we represent parallelization in a language like Java that was not designed for parallelization? Second question we ask is how we define or how we identify the methods or the Java code that we want to offload. And the third question that we ask is, well, and how we interact with the optimizer, how we can be smart in scaling and so on. So for each of these questions, we expose data structure in the API level. So let's start with the beginning. How do we express parallelization in Tornado? Well, there are two ways, and as a developer, you can choose. For Tornado itself, it doesn't matter what you choose, okay? It's depending on your experience in GPU programming or FPGA programming. So the first one is the easiest one, is via annotations. Tornado has two, add parallel and add reduce. If you're coming from OpenMP or OpenACC, this looks very familiar to you. In fact, these annotations annotate sequential code, Java code, right? We believe this is more suitable for non-experts on GPU compute. It doesn't force you to think about how the execution model of the GPU is going to be, right? Or is represented. The second API that you can use to represent parallelization is through a lower level API, what we call kernel context. And through the kernel context, as you can imagine, you can access thread IDs, you can access local memory, you can access barriers, and so on and so forth. So this is a very similar way to how you program a CUDA kernel or how you program an OpenCL kernel or an OneAPI kernel. In fact, you're an expert and you want to port your kernels from C++, OpenCL down to or up to Java, you can use this one. The second is about the definition of the code to be offloaded. Why is this? Well, the typical Java program has hundreds of thousands of Java classes with hundreds of thousands of Java methods. Which ones should I offload? Well, we identify the methods to be offloaded with the task graph API. Okay, I will show you in detail an example later on how this is done. It's very simple. And the last one is about execution plan that interacts with the optimizer, as I mentioned. So let's go in detail about each of these components with an example. I'm going to use the same example I show you in the performance evaluation, the matrix multiply, because it's easy to understand, it fits in one slide. But you can apply to any kernel that is supported in Tornado. We have a suite of examples and benchmarks that you can run and take a look. So just remember the matrix multiply, we have two matrices. We need to traverse each cell of the matrix, and what we do is basically a dot product. Okay, so we multiply the row by a column, and then we sum all the elements. I'm not going to use the standard, the canonical example, nothing clever here. So if I write it in pure Java, this is Java, nothing related to Tornado. We have something like this. We have a class compute, for example, and a method called MXM, or matrix multiply. And we have the traditional 3 nested loops and the reduction in the innermost loop. So to include Tornado, to parallelize the application, let's use the parallel annotation mode, okay, the annotation mode. What we do is to add an annotation in the parallel loop. In the matrix multiply, the 2 outermost loops can be parallelized, and we add the add parallel. This is very similar, if not the same, as OpenMP. I believe OpenMP will have the pragma, blah, 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 but basically it has very similar, a lot of similarities, I mean. The second thing we do, as I point here in the slide, is the data structure have here pointing matrix to the float. There are a lot of data structures that Tornado offers to the user. We have vectors, arrays, matrices, volumes, vector types, etc. So why is this? Because these data structures are stored off heap. So Java Virtual Machine, remember, is a managed runtime language, and everything goes to the heap, the Java heap. So in order to avoid problems with the heap, actually the first versions of Tornado, we have everything on heap, and we switched recently. So there is a new technology in Oracle, well, in Java in general, called Panama array and Panama segments, and those arrays are stored off heap, so we don't interact with the garbage collector. But if you want to use on heap, Tornado is still supported, so you can decide which one. I highly recommend to use the Panama because we apply extra optimizations on top of it, like unify memory or share memory, things like that. Now, remember that we have two ways to express the kernel. The second one is using what we call the kernel context. And if you know CUDA, OpenCL, OneAPI, this is kind of one-to-one mapping with the easiest matrix multiply. You can access also local memory, barriers, and so on here, right? So it's very simple here. And as a developer, you can choose either one or the other. So then you identify your methods to run via task graph. And here I show you an example. You create a task graph, you give a name. Names are useful because you can change at runtime the device, the accelerator, in which the application is going to run. So let's say you run for a while on GPU 1, and then you switch to GPU 2. You don't have to restart your application. Tornado can do it, okay? And you identify that. You do that by using the identifiers that we put in here, the task graph identifier and the task identifier. So the task graph contains many tasks, could be one, in this case is one, could be many, okay, as many as you need. And the syntax is as follows. So first one is the name that you put to the task, and the second parameter is called compute .mxm. In this case, it's a reference to an existing Java method. That means class compute method mxm. So if I go back to the example, is class compute method mxm. And the rest of the parameters is exactly the parameter for this function call. Okay, we have the data already expressing probably with Panama arrays or Panama segments. We pass that over there. And in between, you see that it's transferred to device and transferred to host. I think it's self-explanatory. This indicates that data that needs to be transferred from the host side to the device, and the results are expected, so you transfer from the device back to the host. Additionally, we have a flag to indicate if you run this expression multiple times, do you want to copy every time, or you want to copy just the first time? So you can indicate that through that flag, okay? One thing I want to mention here before I continue, this is just the declaration, data declaration that you're gonna use and the code you're gonna run on the accelerator, but does not run absolutely anything, does not compile anything, okay? To run it, you need to create, as I mentioned before, an execution plan. And to create an execution plan, we create it through a snapshot of the task graph, and then you can call directly execute. If you call directly execute with any other function call in between, what it does is it applies the default device with the default heuristic that Tornado has. That's what I did. By the way, that's what I did for the first example I showed you at the very beginning, the performance evaluation of the matrix multiply. I just run it with as default, let's say. But you can interact with the execution plan. You can enable warm up, for example. You can enable the profiler. You can enable dynamic reconfiguration. I will explain in a bit what it is. You can enable batch processing in here. It's very powerful. And in the future, expect to add for us to add many more functionality in here. So what is dynamic reconfiguration? This is a key feature in Tornado, and I haven't seen this in any other project related to this. What it is a feature in Tornado that allows us to evaluate the performance and pick the best based on a policy, right? So let's say you have two GPUs, GPU 1, GPU 2, and you have an FPGA, and you want to offload some code, and you want to run for performance, but you can think, I have two GPUs and FPGA, which one I should pick, right? Well, it depends on many things. It depends on the input data size. It depends on the representation of the data and so on, granularity and so on. So this feature in Tornado, you enable it and allow us to answer this question. What Tornado will do is we perform an evaluation for all reachable devices for you, and it will pick the best depending on the policy. Policy could be performance, low latency, and in the future, we're working right now on adding energy. And then from that point on, okay, if you rerun again the same expression, it will switch to the device that was already reconfigured by itself. Another feature is the batch processing. Let's say you have to process, 50 gigabytes of data on a GPU that has 1 gigabyte. So you can do it your own. You can split your data your own, and that will work. But Tornado has the feature of doing everything automatically. You just enable batch processing, you pass the data, the maximum amount of data, and Tornado will do the splits for you and run it for you. There are a few limitations though, only for 1D kernels and so on. But as soon as you can live with these limitations, it works really well. This is all I want to mention regarding the APIs. We have some documentation online, as well as the public repo, the whole TornadoVM project. And we have a video recently that explains in detail every function of the programming model with examples and so on. So if you want to expand on this, just take a look. Having said this, let's talk about something new that we have been working on for the past months. Since TornadoVM can run standard OpenCL, CUDA, and SPV, why not plug it in with other frameworks that offers this bridge? One of them is the OCK, the One API Construction Kit. I'm gonna show you a bunch of results, information, etc. I have a blog post that basically we explain in detail how to get started with One OCK, compile it down, compile Tornado, and run all the examples step by step. So I'm gonna focus on the high-level picture, and I show you directly the results. So OCK is a framework that allows us to implement functions to run on custom accelerators. Okay, parallel functions that are going to run on custom accelerators, for example, for AI. But OCK also includes an OpenCL bridge to run on CPUs, and you can run it with Intel CPUs, but also on ARM and even in RISC-V. So why not to run Tornado on these platforms, right? Because as far as I know, apart from, I think Pockle has the ability to run on ARM, not sure if RISC-V, but there are a few projects that can do this, right? So what we did was to plug in Tornado. We extend Tornado to be able to communicate with OCK and be able to run on these devices. And I'm gonna show you a sneak peek on performance that we get using this. Again, all the details are in this blog post. And here, let me explain this graph. So I run the same example I had before, the matrix multiply, okay? And I run with different versions. On the x-axis, I show the input size, input matrix size. And on the y-axis, I show speed up against Java single-threaded, but warm up. So it's the fastest Java single-threaded. And I have a few versions that I compare with. The first one is the Java parallel streams. So it's using the whole course plus the Java G compiler, what it does probably will vectorize the code and so on. And then the last two, the green one and the blue one, is Tornado running with OCK, one API construction kit for OCK for CPU. And the last one is TornadoVM running with one API, the binary for one API for the CPU. So all of them are running exactly on the same CPU. This is a i9 processor, 13 gen. So in theory, we should get the same performance. However, that's not the picture. So if we take a look at the data and the performance plot, for small data size, Java is doing a really good job. Okay, makes sense. So we need a lot of data to be able, the cost of offloading essentially. But as soon as we increase the data size, well, one API gets faster, but also the one API construction kit gets faster, right? And with the largest data size, it's actually 52 times faster than the Java sequential, and I think 4 to 5 times faster than parallel streams on the same CPU. That's good. There is a bit of performance gap, 66% performance gap between the one API construction kit and one API binary. So I talked to CodePlay engineers. It seems like, okay, this is expected from them. One API construction kit is open source, and I honestly believe that this could be better with time. So it's a good approach to get into Tornado as a default OpenCL implementation, in my view. So let me show you the same performance graph, but with different data. So to reproduce this, what I did was to run 100 iterations, all the combinations. Why? Because Java, Java starts in the interpreter, bytecode interpreter, and then slowly, it's gonna compile the code until you get the fastest code. So you will see this transition. Also in Tornado, the first time you run the expression, it will compile down from Java bytecode down to OpenCL in this case, because we use the Intel CPU with OpenCL, right? And then from the second iteration, you get the fastest code because we have in the code cache already installed. And we can see this from this graph. So this graph shows runtime distribution. So in this case, the lower the better, measure is in nanoseconds, to run each matrix size, okay? To run each application. And the first one is the Java single-threaded. The second, the green one, is Java with parallel streams. Okay, it's multi-threaded. And the last two is Tornado with one API construction kit, OCK. And the last one API with Tornado with one API. So as we can see, let's focus on the small data size, 256. The first iteration, even the Java single multi-threaded, is very slow compared to single-threaded, right? Single-threaded is doing a really good job. What we get from this is, if you're gonna run only one time, stay with Java multi-threaded. Stay with Java single-threaded. They do a very good job. If you run more iterations, for example, in the case of OCK, 256, the second already gives us a lot of speed up compared even to Java multi-threaded. And same situation applies for bigger data size. Just let's focus on the last one, for example, the 2048. Even with JIT compilation included in it, is already faster using either one API or OCK compared to parallel streams, which is good. Okay, so this is in Intel, but one API construction kit can also run on ARM. So what do we get in ARM? Well, the situation is a bit different though. So on ARM, I show here a performance graph. Here is performance against single Java thread. So the higher, the better in this case, okay? And we don't, as far as I know, there is no binary, correct me if I'm wrong, there is no binary to run one API binary for ARM. So I didn't have this comparison here. Probably I can get the C++ compiled down to ARM, but I didn't do the test. So in this performance graph, I only show Java streams and TornadoVM with OCK. What do we get? Well, Java is doing a really good job, even for medium data sizes. Only with the largest data size, OCK is running 18% faster than Java. Why is this? Well, I talked to CodePlay engineers, and it seems like, first of all, Java is optimizing very well this code for ARM processor, and it's using SV vector instructions under the hood. And as far as I know, after talking with CodePlay, I think SV instruction support are missing from OCK. But if they include this, I believe that's a huge jump in performance in the near future, right? Okay, good. And what about RISC-V? Well, I don't have performance to show because I don't have a RISC-V platform that would be cool. I mean, if you know RISC-V, it's very hard to get these days. But OCK comes with an emulator, so you can run it in emulation mode. So let's do that. I'm gonna show my screen. Just a second to switch screens now. Yeah, hopefully you can see the screen now. And I'm gonna run Tornado, first of all. This command, Tornado does devices. So this is my PC, okay, desktop. And if I run this command, this gives me all the information about the devices that I can use myself on this setup. It says you have two drivers or two backends. One is SPV backend, and the second is OpenCL backend. Let's focus on the OpenCL backend. I have access to an NVIDIA RTX 3070, and that's identifier in the Tornado runtime with 1:0. I also have the Intel integrated graphics, a compute aorta. This is OCK to run on the Intel CPU, okay? And with this ID, 1:3, I have compute aorta for RISC-V. So let's do that. Let's run the example I show you, the whole presentation, the matrix multiply. This is already open source, so you can run this command. Let me explain what is in here. I'm gonna run Tornado. I'm gonna pass this flag to say, this task, okay, change device, okay, 13, 10. That's an easy way to experiment with different lines. But you can do it also in the source code if you want to. I'm going to enable some debug informations. For example, give me the platform and the threads that you deploy, bring the generated kernel from Java bytecode down to OpenCL in this case, and the example I'm gonna run is in this module, and this is the code I'm gonna run, this binary. So let's start with 1.0. Why 1.0? Because that's the NVIDIA 3070. So if I run it, internally it's gonna run a lot of iterations because I compare with peak performance. Okay, I run, I think, 100 iterations or a bit more. So every time I run, I'm gonna get this pop-up message saying, hey, you run on this platform, with this amount of threads and this block of local threads. And let me show you the first iteration here. If I go up, there are a lot of runs. The first time we run, it prints, because we use the print kernel, it prints the generated kernel. It's very ugly. Very ugly because Tornado, the compiler is SSA representation, and the code emission is also an SSA. But as in a glance, we see that loop interchange was applied already FMA instructions, probably a few other optimizations as well, and so on. Right, so if I go down, I can see now that Tornado is 300 times faster, 380 times faster than Java, and more than 10x compared to Java's multi-threaded, which is quite good. But remember, I can also change, let me clear the screen. I can also change the device. Let's use directly the RISC-V accelerator, and that one was 1.3. So let's do it. So if I run 1.3, I already have the debug information from OCK, so we will see more information even. So if I run it, oh wow. So we have, first of all, RISC-V code, and we have vectorized RISC-V code. That's really good. That's coming from the OCK, by the way. Eh? So the majority of the heavy lifting is through the OCK. And we see interactions with HAL. That's the code play implementation. I believe is heterogeneous accelerator. So we can see the interaction between Java and the OCK, memory allocation, kernel execution, and so on and so forth, which is quite good. So we're running on RISC-V. But not even that, let's not stop here. We can also run Python applications. And I'm gonna run a Python program that performs matrix multiply. It's essentially Python, okay? In fact, what it does is the Python program invokes a Java program, not a Java program, a Java kernel. But everything else is just pure, okay? And we can run it with Tornado, and I'm gonna use exactly the same device as the RISC-V. Will it work? Let's see. So if I run it, first of all, the bootstrap is a bit slower because the Python has more overheads to start the bootstrap. But as we can see, we're running a Python application on the RISC-V accelerator, and it's even generated vector instructions. Again, this is the heavy lifting is coming thanks to the OCK, essentially. Okay, so let's stop the demo here. Let's switch to the presentation. Now I'm gonna talk about how different technologies in TornadoVM has been useful not just for Tornado, but also for other people, other projects. So one of them is called the SPV Beehive Toolkit, or Beehive SPV Toolkit, actually. What is this? So when we developed the SPV backend in collaboration with Intel, you know SPV is binary. And well, we didn't want to write binary from Java. So what we did was to create a framework that does that for us. And the framework uses, essentially, it's like a functional programming style of things. You can compose functions. Actually, what you do is you compose SPV kernels. And it's very easy to compose those kernels, as soon as you know the instructions to generate, of course. But we totally put this as a standalone tool, and we put it, open source it, and it's online. And there is a new project called OpenJDK Babylon project. This is a new initiative from Oracle to bring GPU compute within the Java platform. What it means that hopefully in the future, Java 30, for example, in a few years, GPU compute will be part of the Java platform itself. This is something similar like one API. You get legal C++ code, and you have implementation you can run on GPUs. So this is something similar. And what is interesting is that some collaborations in there, Intel contributed to the SPV backend, and it used the SPV Beehive toolkit. So that's a success for us because it's something that we create within academia, and it's used right now in industry. So it's quite good. I will talk about a bit more in a minute about this. And the second project I want to talk about is the Level 0 GNI project. So again, when we port SPV can be dispatched either through the OpenCL or the Level 0 API. So we did a port for GNI, Java Native Interface, to dispatch the code in low level and interacted with Java. And we also put a standalone project for it. And we have some proof of concepts just using this library to accelerate LLMs applications, Llama 2 in our case. So let's talk about that briefly before I conclude the presentation. So for the SPV toolkit, is, as I mentioned, is open source and allow us to run in a kind of functional style like of things, SPV kernels. Okay, there are plenty of examples in the website, and as I mentioned, it's being used by a Babylon project. So we have a paper, and the interesting thing about this toolkit is that the toolkit itself is auto-generated using specification from Kronos, okay, the SPV specification. So for us, switching from SPV 1.2 to 1.3 is just one click, changing one value. In fact, we have done this experiment. So for now, because as far as I know, Intel supports SPV 1.2, we have 1.2. But in the future, of course, we will adapt. And we have a publication in which we talk about the internal of this library if you want to, to know how this is done. So let's talk briefly, before I conclude, about this Level 0 GNI library and Llama to accelerate LLMs. So again, this library is just a bridge from Java down to C, C++ to dispatch Level 0 applications. It's open source and you can use it. So what we did was the following: to integrate this library in a pure Java program for running Llama 2. We have some studies, okay? We have one of my colleagues, Michalis Papademetriou, has a blog, actually, if you want to follow along, trying to accelerate with Tornado Llama 2, right? And we got some speed ups, but not impressive, right? And one of the things we have to take care is that, well, if you analyze the application, the bottleneck actually comes to one kernel, matrix vector multiply, but you call so frequently with not very large data set that becomes the bottleneck in memory bound rather than compute bound. And Tornado, as it is right now, does not support shared memory. So before jumping directly to shared memory with Tornado, which has some implication because how Tornado is built, we did a study previously with just GNI library and say, okay, if I have this buffer in shared memory, how fast I am? So let's do that. We did evaluation with an ARC 7070 GPU, and Intel graphics, the same as that is included in the i9 processor 13 Gen. To show you the performance plots, we have this. So we execute this with 3 different models: 15 million parameters for Llama 2, 14 million parameters, and 110 million parameters. And the y-axis shows throughput, tokens per second, so the higher the better. And here I show different versions: the Java version, the Level 0 GNI with the ARC GPU, the Level 0 GNI with the integrated graphics, and the last two correspond to Tornado. Tornado on the ARC GPU and Tornado on the Intel integrated graphics. So remember, the higher the better. Let's focus on the small one, 15 million parameters. As we can see, Java is doing a very good job for accelerating the small models, right? And the rest are kind of on par. It's a bit slower, but it's kind of on par. It's actually 1-2% slowdown compared to that version. This version is not even the fastest Java. Java does a very good job of optimizing and vectorizing the code, but it could be even better by using explicit vector instructions, for example, in Java. But as soon as you increase the model size, the Level 0 gets some extra performance, right? Especially the medium model and the large model. And we see that Tornado is kind of on par, but the ARC GPU does not have shared memory. Why is this then? Well, the kernel we took for the Level 0 port is using a tune loop and roll, right? That Tornado doesn't have, and that's where the difference comes from. However, the big difference comes from the integrated graphics. And we see a huge gap between the Java GNI using the integrated GPU and Tornado using the integrated GPU. And it's actually losing kind of close to 100 tokens per second, which is a lot. So what do we take from here? Well, first of all, Java is not that slow, even, to run small the configurations, right? And even larger configuration is not that small. Second of all, because of Tornado double buffer approach, this is a limitation when we run this type of applications within Tornado. So now the next step for us in Tornado is to actually implement this in the right way to achieve high performance. And in the case of the integrated GPU, it's losing, okay, as I mentioned before, 100 tokens per second. But one thing I want to mention is in Tornado, you could also run, because the results are correct, you can also run LLMs, and I said LLMs, which is a huge achievement for us. Okay, so that's all I want to mention. Just to wrap up, today I show you TornadoVM, a framework to run and offload Java programs written in Java as close to Java as possible with a few tweaks and annotations, and be able to accelerate on heterogeneous hardware. I show you the integration and the connection with OCK to run on ARM and RISC-V, even with a demo. And some of the technology, just we finalize this, some of the technology can be used not only for Tornado, but also for other open source projects like Babylon or for running LLMs and so on. So with that, I conclude my presentation.